Hi everyone. In this video we look at a couple of special cases and an application problem. The first special case is what is called holes in the graph, which you have to be careful about. So here's how we go about finding that. We follow the process that we established last time. So we factor. In factoring, notice that the top and the bottom have the same the top is already factored, right? So the bottom is now x times x minus 3. Now here, immediately, what you notice is where x minus 3 can be cancelled, right? So here we kind of stop the procedure and we say that x minus 3 cancels out. When it cancels out, this actually becomes 1 over x. So we know how to plot this already. Right? We know that the graph for 1 over x is simply this. However, we have to be careful here. Okay? This cancellation here is oversimplifying certain things, right? Because the function that you're working with is actually x minus 3 over x squared minus 3x. It's not the cancelled version, right? So this function as it is, right, it has a domain of real numbers except 0 and 3, right? So which means that for this particular function, the input cannot be 3. So what we do is we look at x3 here. That's going to erase the whole thing. And we're going to put a hole here. So there's a hole at x equals 3, meaning that there's no output at x equals 3. Okay, so even though we cancel the x minus 3 term, because the original form of the equation or of the function has that, we have to be careful about it because it means that 3 cannot be an input. Right? In the simplified version of the function, 3 can be an input, but that's not what the original function was. And that's why, while we can do the cancellation and draw 1 over x because we know how that looks like, but we still have to introduce the hole at x equals 3 to kind of preserve the information about the original function, which is that the original function cannot have 3 as an input. The second special case is what I was talking about a long time ago in one of the videos, saying that asymptote can be any line that the function approaches. But the simplest cases are when these lines are vertical or horizontal. However, they can be slant asymptotes. And this will happen if the degree of the numerator is larger than the degree of the denominator. So if you're plotting a rational function and you notice that the degree of the numerator is larger than the degree of the denominator, then that automatically tells you that this is going to have a slant asymptote. And let's see why that is so. So because this is in this form, what we are going to do is first we are going to divide them. Right? To divide them, because of the way these are, I'm going to choose to use synthetic division, which will give me 3, -1, -3, -8. Right? 3, -1, -3, -8. So this tells me that the quotient is x minus 1 and the remainder is -8. Right? So this tells me that x squared minus 4x minus 5 over x minus 3 is actually x minus 1 minus 8 over x minus 3. Okay, so this is the function. Now, we notice that as x goes to infinity or becomes large, this 8 over x minus 3 becomes 0, and we are left with x minus 1. So that is going to be the asymptote, right? Because what this is saying, y equals x minus 1 minus this rational function, is saying that as your input becomes larger, this second part becomes irrelevant because it's 0, and then the function pretty much behaves as the straight line x minus 1. So how are we going to plot this function? Well, we plot this function 8 over x minus 3, right? 8 over x minus 3 has a vertical asymptote at x minus 3, and this is just a transformation of 1 over x, so it kind of goes to 0. However, at infinity now, we need to plot y equals x minus 1. What does y equals x minus 1 look like? That's a slanted line. It goes through x1 and y negative 1. So that is my slanted asymptote. Okay. All right. So we still have to do a few things about intercepts, right? So when x is 0, y is 0. So it goes through this point. Y is 0 when the numerator is 0, right? So x squared, what is it? Minus 5x minus 5. If you factor, that's negative 5x plus x minus 5. X minus 5 plus 1 x minus 5. X plus 1 x minus 5. That's at 5 and negative 1. Okay, so we have these intercepts. Now these are vertical asymptotes. But it approaches, as it goes to infinity, this gets closer and closer to that line. So that's what that is going to look like. And then there's a y-intercept here and this intercept here. So let's see what's happening here. When x is 0, when x is 0, this is actually 5/3, right? So this is not correct. This is negative 5/3, so it's over here. That's why, yeah, that makes way more sense now. Because that means it goes down from here, here, and it approaches this line. So it kind of does that, going up. Okay, so it can get a little tricky to draw with the slant asymptote, but with, as you do more questions, you get more used to it. Doesn't have to be accurate, but it just has to show that as you go to infinity, right, on the input scale here, this thing gets closer and closer to the slanted line, which in this case is x minus 1. So that's the second special case. You can have holes in graph, or you can have slanted asymptotes, and in which case you find the slant asymptote by doing this division of the polynomials which you have learned. Now let's look at an application problem. One application problem is from electricity or resistances. So the first part is just information that you don't have to know or have any background in. It just says when two resistors are connected in parallel, their combined resistance R is given by 1 over R equals 1 over R1 plus 1 over R2. Now it says suppose a fixed 8 ohm resistance is connected with a variable resistance of x ohm. Graph the combined resistance R as a function of x and interpret the result. So this says R1 is fixed at 8, R2 is variable at x. So based on our relation, 1 over R is 1 over 8 plus 1 over x. So we want to solve this. To solve this for R, take the LCM, 8x. So you have the LCM, you multiply, divide by the missing bits here. When you do that, you get x plus 8. Then you cross multiply. and you get r is 8x over x plus 8. These are already factored, right? So intercept x equals 0, r equals 0. So r here is representing, you can think of it as y. The other intercept happens when y is 0 or 8x is 0, which gives you x is 0. So 0, 0 is the only intercept. Asymptotes. Vertical asymptote happens when x plus 8 is 0 or x is negative 8. Horizontal asymptote is y equals 8 over 1 or y equals 8. Then the plus minus values, the two values are x equals 0 and x equals negative 8. Let's pick some value. Probably easy one to pick here is 1. 1 is 8 over positive. So it's positive here, which means it's negative here, and then it's positive here. Now let's put this information together and plot. What do we have? It goes through 0, 0. There's a vertical asymptote at x equals negative 8. There's a horizontal asymptote fixed at y equals 8. Beyond 0, it's positive. Between 0 and negative 8, it's negative, so it goes down here. And it's positive somewhere here. Now, however, since your r is not ever negative, right? So we just plot the positive part. So the positive part is that. That's y equals 8. So what this says is, as x is increased, the total resistance caps out at 8. Okay, so this is saying that if you have two things in parallel and one is 8 and the other is x, if you keep on increasing x, it's eventually just going to equal 8. Physically, what that means is, you may have heard the term that electricity or current follows the path of least resistance. So if you keep on increasing x, you're kind of like blocking here. It's kind of like making an open circuit, and you're just saying that the resistance is too much here. So all the current will try to flow in through the 8 ohm resistor. And so eventually it will behave like there's just one resistor, which is equal to 8. However, as you make x smaller and smaller, the resulting resistance becomes smaller and smaller. Okay, so this gives us a control over how the current is flowing, right? In particular, if you want the control to be such that the resistance at infinite value becomes fixed at like 8. Okay, so because of their inverse nature of relation, whenever you're solving these kind of problems, they end up becoming a rational function, which means they have a vertical asymptote which should ideally be in the negative range so that it's not something that's physically possible, and have a horizontal asymptote when they are in parallel so that there's a limiting value beyond which the resistance does not increase. That brings us to the end of the topic of rational functions and how to plot them. So you can go over the videos, try some of these problems on your own, and then compare it to the solution, and also do the worksheet and homework, and that should be good. Okay. Thank you, everyone.